today let me introduce what is a perfect number. Use 6 to example. The 6 proper divisors is 1, 2, and 3. Right? Okay, so 1, 2, and 3. Okay, so 1, 2, and 3, we plus them together. 1 plus 2 plus 3. It's that all of the proper divisors is excluding the 6 himself. Okay, so 1 plus 2 plus 3, you can get 6 himself. So that means 6 is a perfect number. Okay, so, and you can have a try like 10. Its proper divisors excluding itself is 1. And then you can say plus 2 plus 5. And you can only get 8. So 8 is not 10 itself. So 10 is not a perfect number. Now let's see. Actually, the Euclid find out a way to find all to find every even perfect number. And what's that? The way first you can 1 and you double it, 2, then you double it 4 and 8, then double it and so on. It's 8, 16, then 32, then 64. And then you plus all of every number together. And first is 1 plus 2. And you come out equal to 3. And 3 is prime. So we can use 3 2 times 2. 2 times the last number and last value in here. In the series calculating ring here, right? 2. Okay, so and when you time them together, you can get 6. So 6 is the first perfect number. And when you plus the 4 plus 4, you can get 7. And 7 is a prime. So 7 times 4, you can get the next perfect number, 28. And then you do it again, like when you plus 8, then you can get 15. So 15 is not a prime. So we do it again. And we plus 16. Then we can get 31. 31 is a prime, so we can use 31 times 16. So we can get a next perfect number, 496. Okay, so this is the way. And actually, here is a very funny thing. Right, okay, let's see. First you can find out 6 is equal to 1 plus 2 plus 3. And 28 is equal to 1 plus 2 plus 3 plus point plus 2, 7. And 28 like this. So then, and 496 is equal to 1 plus 2 plus 3 plus point plus 2, the 31. And every of them, actually, we can change to 1 to the third plus, and you see 6. 6, you can't change it anyway. And to 28, from 28, you can change it to 28. You can change it to here. You can change it to 1 to the third plus 3 to the third. Actually, that's cube, right? 1 cube plus 3 cube, and 496 is 1 cube plus 3 cube plus 5 cube plus point. Actually, that's odd number cubes, and plus to the and plus to the. Sorry, I got it wrong here. Should be just plus 1 cube plus 3 cube plus 5 cube plus 7 cube. Okay. So let's see. Now let's see. Actually, there is another funny thing. Okay, funny thing. Let's clean this out. And I'll find it. Of course, when you write it in binary, when you write it in binary 6, you can't change it. And you see, 28 write to binary, it can change to 28 write to binary, it can change to 111 111 0. And when 496 turn to write into binary, you'll find out it is 11111 0. Okay. So actually, you can find out here, 28. 28 is equal to 2 to the 4 plus 2 to the 3 plus 2 to the 2. And 496 is equal to 2 to the 12 plus 2 to the 11 plus point plus 2 to the 6. Like this. 2 to the 6. Okay, so actually, I'm sorry, I already wrong here. It should be 2 to the 8 plus 2 to the 7 plus point plus 2 to the 4. So of course, in another word, you can say it is a pernicious number or practical number. Now let's see the next one. You can write it to 6 equals 1 plus 2 bracket 1 plus 2 bracket times 2 to the 1. And you can write it this. And 28, it can equal to 1 plus 2 plus 4 bracket times 2 to the 2. And like this, so we can get 496 is equal to 1 plus 2 plus 4 plus 8 plus 16 times 2 to the 4. Okay, so actually you can got it. Now let's see. Right in this part you can see the 2 to the 1 plus 2 to the 2 plus point plus 2 to the n minus 1, then plus, and then because you don't know what is n, so you don't know what is this whole thing. So actually we can say that's equal to t. So it was t, and both sides we can times 2, so we can got, and sorry, here's the 1 plus. Here's the 1 plus this one, okay? And now we can both sides times 2, so we can got 2 to the 1 plus 2 to the 2 plus point plus 2 to the n minus 1 plus 2 to the n. That is equal to 2 times t. So actually, we can minus them. We use this to minus this, so we can this or all cancel out. So actually, we can got 2t because 2t minus t, so t. So actually, we can got t equals 2 to the n minus 1. So we can got 2 to the 1 plus 2 to the 2 plus point plus 2. 1 plus this one, n plus 2, 2 to the n minus 1 on the first one, so we can change the t. We can substitute t to the 2 to the n minus 1. So this is equal to 2 to the n minus 1. Okay, so we got that. So actually we got this one, so we can change it. actually we can change this part to 6 is, we can change it to 6 equal 2 to the 2 minus 1 times 2 to the 1. And here we can times it, we can turn it to 2 to the 3 minus 1 times 2 to the 2. And this can change it to 2 to the 5 minus 1 times 2 to the 4. And then actually you can find out here, and actually you can find out here is always prime, and here is always prime, this prime minus 1. So actually that means you could find out something that means is the perfect number is equal to, and we said p is the prime, so we can say 2 to the p minus 1, and write the whole thing times 2 to the p minus 1. So now that you can find out the perfect number is equal to this one. Actually, in the Euclid's way, you see, because the Euclid's way is the perfect number equals 2 to the p minus 1 times 2 to the p minus 1. And here it has a Mersenne prime. The Mersenne prime is in this part. So right here it needs to be when p choice a prime, and this part needs to be a Mersenne prime. And actually you can do things. The Mersenne prime is when this part is a prime. So that is the Mersenne prime. And here is a prime, here is an even, right? This is 2 to the p minus 1. So here is an even number, and so you can get the perfect number. Actually, this means the Euclid find out all of the even perfect numbers. And now Nicomachus has 5 conjectures he believes to be true, but he's not trying to prove it. Now, the 5 conjectures is, the first one is the nth perfect number has n digits. And the second one is all perfect numbers are even. And the third one is all perfect numbers is end in 6 and 8 alternately. 4 is Euclid's algorithm produce every even perfect numbers. 5, they are infinitely many perfect numbers. And now let's see. And first we proved the first one and the third one, first and third conjectures. First we can list out, we find out all of the perfect numbers, and this is what p choice. And the perfect number is 2 to the p minus 1 times 2 to the p minus 1. So, and first when p choose 2, and then 6, 3, 28, 5, and you can got 496. Okay, so then when it's 7, it is 8128. And when it's 13 is 33, 55, 0, then 3, 33, 6. Okay. And the 17, when page was 17, so, and you can got 8, 85, 89, 869, then 0, then 56. Okay, so actually when we write of them, the first conjecture is the nth perfect number has n digits. When it's the fifth perfect number, there has no 5 digits. And now we disproved Nicomachus' first conjunction. And right here we see 6, 8, 6, 8, 6, 6. And so that means we disproved the Nicomachus' third conjunction. It's all perfect numbers ending 6 and 8 alternately. Now let's see Ola's genie thoughts. First, let's see. And actually, Ola find out is the sigma function. Sigma function you can find out actually it's just a little bit change. First, sigma, we can write sigma 20. Have an example, sigma 20. And that's equal to, first you will find out that's equal to 1 plus its or proper divisors including itself, like including 20 right here. So it's 1 plus 2 plus 4 plus 5 plus 10 plus 20. So we can get here is equal to 42. So actually, because you find out it just including itself. So actually, you can find out the sigma function, sigma. So that you will find out the sigma, if that sigma a perfect number. So the answer is 2 times of the perfect number itself. Actually, you can find out here. Actually, the sigma function is a very strong weapon. Because you can find out here you can find out because that's 1 plus 2 plus 4. So actually you can find out it's 1 plus 2 plus 4 times 1 plus 5. So actually that means that is the sigma 2 to the 2 then times sigma 5. So actually, we can change 20 to its factors, and we can sigma every factors. So then, actually, that means we can find out. So if we say n is equal to p1 to the a1 times p2 to the a2 times point times times pn to the an. So we can get sigma n is equal to sigma p1 to the a1 and then times sigma p2 to the a2 then times point times to the sigma pn to the an. Okay. So now we can get this one. So let's see next thing. And now Ola is going to find the problem about when n is equal to odd. So that means actually if the ordinate perfect number exists, there must have a special form of it. So first let's see. First, if like n is odd, n is a odd perfect number. So actually we know two things. Is n first n is odd, and the next thing is sigma n is equal to 2n. So you get the 2n. So now actually, so that means the sigma, this part, right? Sigma P1 to the A1 times sigma P2 to the A2 and times point times sigma to the sigma Pn to the An. Okay. So let's see. Actually, you will find out when you have an example, because here is all here everyone is prime to a value, right? Okay, a prime to a value, you can just calculate. Example, you can say 7. If there's sigma 7, you can get 7 plus 1. So that's odd plus odd equals even. So actually, you can find out when you see sigma. So when you find out sigma, 7 to the 2 is equal to 7 to the 2 plus 7 plus 1 is equal to so that's equal to 56. Okay, so actually like that you can just find out. So that's so actually you'll find out that is odd. That is odd plus odd plus odd. So that is odd. So you can find out if that is odd to a value, and this value is also odd. So you can find out, you can get sigma 8. You can find out the answer is even number. So when is the a prime to the when a prime to the even number, so you can just got, when you sigma it, you can got a odd number. So you can get odd number, right? Okay, so actually we can got, P is prime. Okay, so sigma P to the 2k plus 1, and it's even. And if that's sigma P to the 2k, so you can get is odd. So that's what I talk about, right? Okay, so that's odd. Okay. So now let's see. So actually from this we can just got n. N is equal to Pj to the odd. Of course, because why? Why? Because at first you think, sorry, I write something. Here is equal to 2n. And you see, n is odd. This is 2, so of course the both side only has one even factor 2. Right, this part and this part only have one even factor 2. Right? 2. This part has one of the 2, and this part has one of the 2. So that means this part you can change it to. That makes this part you can change it to n is equal to Pj to the odd, and bracket P1 to the K1, then times P2 to the K2, then times point times P times P to the n, Pn to the Kn, and then bracket to the 2. So actually we can got this one. And you see this one, and actually in this part in here we can change it to another thing, and we can just set it. Maybe we can set it to m. So n At last, you can got, and I just clean it out here. You can got, and last is n equals pj to the r times bracket n bracket 2 to the 2. And actually, you can got this one. And actually, the Ola find three things. The first thing, Ola discovered the eighth perfect number. So actually, the perfect number is, write it out and we'll just clean it. 2 to the 31 minus 1 times 2 to the 30. And that's equal to 2305 8 4 3 0 0 8 1 3 9 9 5 2 and then 1 2 8. This is the eighth perfect number. Now, and Ola find out it. And now Ola proved the problem. Now Ola proved that Euclid's way find all of the even can find out all of the even perfect numbers. And third is Ola proved the problem about the even perfect number. Okay, so now we got it. And okay, so the even perfect number at last we can got n equal ps times m to the 2, and now Ola get a little bit change of it. So we can got n is equal to p to the 4k plus 1, and then times m to the 2. So at last we got this.